is going to be nonlinear control. And another problem. So, I want to keep here 1. I don't want to go more over there because I'm going to get saturated. Saturation, we have no problem, right? Why I want to be here? Because look at here, we see T torque is K flux IA, right? If I want to have my maximum torque, right? If I want to have my maximum torque, it's better to keep it for maximum, right? If this term is maximum, right? So you said I'm going to bring 1 amp, I want to get the maximum possible torque. So this term should be maximum, right? I'm bringing 2 amp, I want to get the maximum possible torque. You should put your key on the maximum value, right? So basically you have better utilization of your system. You know, we don't do flux control that much unless we get to the field weakening. We have to do that one. I'm not going to talk about field weakening, you know, it would be more like motor drive, you know, and those kind of things. But flux control is used, but over the basis. For example, they say this machine, the nominal speed or rated speed for this machine is 1000 RPM. If you are going to go more than that, for example, you want to control the machine 1200 RPM, 1300 RPM, you start to use the flux. You start to, you call it flux weakening. You start to weaken the flux. You see, you cannot go, you put it in the maximum, right? You cannot go this way, right? If you go this way, it's very saturated, right? They call it flux weakening. Where you go more than the base, above the base speed of the machine. You start to reduce the flux. Why? Just, I don't want to talk about it, but why? Look at here, K flux omega. Machine has a rated voltage, 220 volt, I don't know, 120 volt. You cannot go more than that voltage. You can be less than that, but you cannot go more than that. So if you are at the rated speed, rated flux, this one is going to be, for example, 212, the rated volt. Now, if you are going to go more than rated speed, so you are increasing this one, right? If you don't decrease this one, this voltage is going to go more than nominal voltage. It's going to kill your machine. So basically, if you go up on this one, you have to go down with this one. You have to reduce this one to keep the voltage constant. If you go above base speed, you keep the voltage constant. You don't go more. But under the base speed, you can go. You can have a variable voltage from 0 to the nominal voltage. So, but just to make it simple, you know, there is a voltage control, flux control, armature control. Armature control is not good because it's going to add more resistance to the circuit. It's going to cause more loss in the circuit. Efficiency drop. Flux control in general is not good because, first of all, we would like to work with the best flux possible, maximum flux possible to get the best torque performance. And the second, the control is nonlinear, right? So this one is the best. If you have looked at the, give you a very quick example here, in the power electronics, I'm sure you're going to see that they have a full bridge rectifier with the thyristors. See, as simple as this one. They put source here, AC source here. If you look at this voltage, and it's the Vs is equal to Vm sine theta. If you look at this voltage, VDC, it's going to be Vm cosine alpha. Alpha is the firing angle of the thyristor. I'm not sure. If you talked about it already, you know what I'm talking. But if you didn't, you know, we will see when it's talking, when you see the teaching. You can control the firing angle of this thyristor. Basically, alpha can go for this system can go from 0 to 180 degrees. So you can move. If alpha is 0, you're going to have the maximum voltage. If alpha is 90 degrees, you're not 180 is going to give you negative voltage. But if you go to 90, it's going to give 0 voltage. So basically, you can control the voltage from Vm to 0. Very simple with a thyristor circuit. This is a pretty old circuit. This is not new. Nowadays, they do with the IGBT and those kind of things. It's been better, you know. But this is a very simple, you know, variable voltage for the motor control. Usually, they use it in the excitation system to control the field voltage. So this is the, now we're going to look at the characteristic of the machine. If there is no see here we look at that one, terminal voltage versus IA, right? This is important for us. How much voltage we have here and how much current is going out, right? This is the characteristic of this generator, VT versus IA. Here when I'm looking at this one, what is important for me? What's the speed of the machine and how much torque I'm giving out, right? These two, omega m versus TL. So if TL is zero, how much is this one? Right? So again, if this machine was ideal, I'm going to give you an example. Let's say I'm walking here, and there is a chain here to my belt, and there is a weight right behind me. I have to carry on that one with me. If I am, halt, I'm walking. I don't care is it 1 kilogram, 10 kilogram, 100 kilogram. I'm going to walk at a speed, walk with constant speed, right? But if it's me, if you put a 10 kilogram there, I'm going to struggle to walk, right? I cannot go fast. The load you are putting over there is going to hold me back. If this motor is very strong, what you're going to see? No drop in the speed, right? If it was rotating with 100 RPM or 1000 RPM, doesn't matter how much load you are putting on this machine. It is a very, very strong machine, right? So there is no speed change, right? But in reality again, based on this equation, it's going to be linear again. TL is increasing, right? So it's going to be linear, but in reality again, it's not perfectly linear because of armature reaction and those kind of things. So this is, what is this? This is a delta omega. How much is it? Right. Now if I change the flux, so I'm bringing it from here, for example, to here, what's going to happen? This point is going to change, right? It's going to come either here or going to go there, right? So it's going to be a bunch of distance, right? Based on how much flux you have, right? If you have a more flux, it's going to be down. If you have less flux, you're going to be up, right? Again, linear. So this is the motor characteristic or torque characteristic for the motor. So for the motor, the omega versus TL is very important. For generator, VT versus I is very important. There are two very important characteristics for motor and generator. And the no load is very important in general, because it's going to tell you how much voltage you are going to generate or use inside your machine. I believe this is the first time we are running this lab. I believe you are going to see this characteristic in the lab, hopefully. When you do it, let me know what you do. Any question here? Yeah.
So for the omega versus torque, is that like what you would see on like the top of like a NEMA V or a D curve?
NEMA what?
The motor characteristic curves? Like
oh no, they're different.
Okay.
Those motor characteristics are different because they depend to how much voltage you are putting there. For example, induction machine, they have class A, class B, class C, class D. It's different. How you put the winding inside the slot, those kind of things are going to be different. This is a general. This is a very, very general characteristic I'm talking about. Here we talked about the DC motor, but in general, for all the motors, torque versus speed is very important characteristic. Very important characteristic. Let me just tell you a little bit more general knowledge. How many we have here about the regenerative braking? Where did you hear? Where did you hear?
Prius.
Prius, exactly. That's a very good example. In electric cars, Just let me tell you what it is. This thing, based on this curves and this kind of thing. I'm going to put torque here, omega here. This is quadrant number 1. They call it motoring quadrant. A speed positive and motor and torque positive, right? You are going. This is the electrical torque, right? So look at here. They should be in the same direction, right? So now you are sitting in the Prius. You hit the electrical brake, not the mechanical brake. What is going to happen? So we see we are somewhere here, right? Either you have some speed, you are using some torque, right? And you are moving. Now you push the brake, electrical brake. What's going to happen? Exactly. You go to this path. See, still your speed is constant. Sorry, the speed is still positive, right? It's not going to be exactly like this. It's a constant speed. Basically, it's going to be like this. It's going to go somehow like this. To stop, you are going to start, the speed is going to start to maybe it's like this. You're going to go here. First of all, torque become negative. Torque has to become negative first, right? Now from here, you're going to go to zero speed, I don't know, whatever. You're going to go here, through a path, right? They call it regenerative braking. When you're braking, what is happening is acting like a generator. Think about it. See, motor, omega m and T, they are same direction, right? As soon as the speed and the electrical torque, they are opposite direction, is a generator. Right? We can think about it here also. Torque is say positive and the speed is negative. Again, this is another mode. For I think they call it. This is another name. I forgot the name. We call it. There is a name for that. Forgot the name. Here they call it. Most of them they are negative. You know what they call it? Can you give me an example for this part? Going back to the electric car. You're going backward, right? Still you're motor, right? Because you're using energy to go backward, right? Both torque and speed, they are negative. They call it reverse motoring. Forward motoring is you are going forward. Reverse motoring, you are going backward, right? Still you are motor. For both cases, you are motor. You are taking the energy to run. Here, they call it regenerative braking. You're changing it from the motor case to the generator case. Here, the same thing. I forgot they call it.
They call it dynamic braking.
Yes, I think they call it dynamic. Exactly. I think they call it dynamic braking here also. But this one, I'm sure they call it regenerative braking. I think this one they call it dynamic braking also. Forward motoring, reverse motoring, regenerative, and most probably dynamic braking. This is a 4 quadrant for a torque versus speed for a motor. See, all this profile of the machine, all the electric car, to be designed, to be working, they have a profile. They design. I worked like 3 years for General Motors and about 4 months for a startup company which is called Coda Automotive. They were in Santa Monica, LA. We had a torque profile to simulate the load behavior. They put that one on the motor. So you have an electric motor, you have an inverter, you have a battery, all those kind of things, and they put kind of torque similar what they are going to see in the road. This is the first step to characterize your motor, your inverter, your electrical system. They put that one there, and they look at your system can handle that or not. For example, they simulate going uphill, very very steep uphill, with a huge torque. They put a very huge torque on the machine. This thing all will be simulated. This is basically a curve like this. When you are going downhill, the torque is going to be negative, right? So basically, they simulate all this kind of thing. They call it the torque profile of the machine. They put that one on the machine. They make sure the machine can handle all those kind of things. And if it's like this, no, it cannot go. None of the electrical they can do this much. It's steep, and they're gonna stop. They're gonna move, But there's a standard. No road is gonna be like this. 90 degree, 90 degree. I'm not sure. No, it's not gonna be like that. Yeah. That one you cannot blame it on the motor, on the car. Then. So before moving to the shunt excitation, I want to talk about the efficiency of the electric motor or generator. So for those of you who are starting, our electronics is a really, really good course. And there is a lot of work in the industry for those when they have good knowledge of power electronics. Take it a little bit more serious. When there is teaching, don't look at it just some chalks on the board, or PowerPoint slide, Think about it a little bit more. What is this? What I can do with this? See how much makes you flexible to do those kind of things. It's a very, very good skill for finding a job. I know lots of you are looking for a job, that's one part. Some of you are here because only the knowledge, to become more knowledgeable, but I think maybe 5%, 10% is like that. But the most they are looking for a job, They want to, so no, I shouldn't say the most, The most they are looking for knowledge and money together, I don't know why when I was a kid, always they used to give us this. I'm not sure, I didn't get my preliminary school in here. But we had a composition, you have to write it, for example, they give you a topic and you should write about that one. I'm not sure if you have it here in the, something like that. Always I ask, knowledge is better or wealth is better? And if you answer well, they're going to give you really low. No, really, I'm offended. Nowadays, they're a little bit more. To me, wealth is better, because if you are wealthy, you can get the knowledge. You can go to best university and educate yourself. But if you are very smart, but still you're very poor, maybe you're not going to get to the very ugly university. I'm saying you're very. That's the thing. To me, wealth is better. I'm not sure what's the rest, but. Always they put this one with a very clear answer, but you cannot answer. I'm saying very clear. But by the field of power electronics is a very good field for future. If you guys want to stay in this field, you want to work in this field, there are lots of applications for power electronics. There are lots of jobs for power electronics application. Could be renewable energy, could be electrical, could be motor derived, could be power supply design. In very good, they have this kind of thing. And it's getting more like a microgrid you talked about. You go to that, they have all. You don't see that one. As I say, Bill is not expert on that part. But there's one box for all of them. It's called inverter. That's the power electronics to connect all these energy sources, non-regulated energy sources, to a regulated energy source. That one is a huge deal, The Schneider Electric is working on that, ABB is working on that, General Electric is working on that. These are big companies I'm talking. There are, I don't know, maybe many companies in US, small one, big one, medium size. They are working on this kind of thing. Take the power electronics a little bit more serious. If you want to do some projects, work on some projects, real projects, to get hands-on instead of just doing calculation. Use the simulation software PC. PC by itself, it has lots of examples. If you go to the directories installed, it has lots of good examples. When you have time, go look at those examples. You see rectifiers, you can see motor control, you can see renewable energy. There are tons of examples over there. You don't have to money. Just look at how it does work. This kind of thing. Some of you want to go for graduate school, maybe 5%, 10%. These are a very good topic to continue for the graduate school. If you are interested in this stuff. Now, before going to the shunt excitation, that one was separately excited. The next one is the shunt or self-exciting. Before going there, I want to talk about the efficiency profile. Let's say we have a generator. Let's go back again. See, if it's the generator, see we have, I'm going to say about the self-excitation. This is a generator, right? And we have a mechanical torque here. And this machine is rotating like this. And we have this electrical here. Right? What is the input power to this system? This is a generator. What is the input power to this system? What is the input power to this system?
Mechanical work. Mechanical work.
Mechanical what?
Work.
Like mechanical power. Yeah. Or work. Yeah. So basically, we are going to have a key input, which is how much? dW dt. How about just say Q omega? Torque times the speed, right? And assume this is a Newton meter and this is a radian per second, right? Is this correct? So that's the mechanical power, right? T omega is the mechanical power. So this power is coming to the machine. Right? What is the first loss you are going to see in the system? Friction. What else? Friction, because this thing has a bearing and those kind of things. It still has some friction, right? What else? Air, right? Air also, when this one is rotating, those air is going to create, some loss. They call it rotational loss or mechanical loss or whatever you want to call it. So we are going to lose some loss here. P rotation. Well, let's call it P rotation. I think we mostly because the machine is rotating. It's called, if it doesn't rotate, there is no loss, right? They call it, that's the reason they call it rotational loss. So what happened now? The power from here came to the electrical side, right? So how much is this power? Can you tell me? How much is this?